Now let's come back to J plus and see what's the action of, what is the result of applying J plus on one of these states. Okay, if I apply J plus on, say, lambda m, now what happens to the J3 eigenvalue? But the lambda eigenvalue will never change, right? It doesn't matter if you apply J plus on it, or J minus on it, or J3, it will not change, right? Because J squared commutes with all the operators, so its eigenvalue is going to remain the same. Okay, so let's first apply J plus on this state, and then apply J3 to figure out what the eigenvalue of the resulting state is. But this, we can use one of the commutation relationship to write as J plus J3 lambda m plus J plus lambda m. Okay, so what are we using? We are using the commutation relationship where we have J3 and J plus is equal to plus of J plus. Okay, that's what we're using. So now the right hand side, we can write this as J plus J3 acting on lambda m, and then J plus acting on the state lambda m, the vector. But this is an eigenvector with eigenvalue m. So we get J plus times m lambda of m plus J plus lambda of m. But this is just a number. This is just a number. So we can, bring it out in the front. And if you do this, we get m plus 1 times J plus acting on lambda m. So what was on the left-hand side? The left-hand side was this thing. J3 acting on J plus lambda m. So this is an important equation. What does this equation mean? It means that if I apply J plus on a state, its J3 eigenvalue increases by 1. Okay? Therefore, I can write J plus acting on lambda m should be proportional to what? What should it be proportional to?
Lambda m plus 1.
Right, because J plus acting on it increases the J3 eigenvalue. Okay. So this is always the J3 eigenvalue, and this is always the J squared eigenvalue. Okay. These are the slots for them. Okay. So we actually will need the constant of proportionality here. That's going to play a very important role. We shall see. So let's give it a name. Let's call it C m plus 1 lambda m plus 1. Okay. So where C m plus 1 is an m dependent non-normalization constant of proportionality. And we shall see it actually depends on lambda as well. But that's not what we're worried about right now. Okay. So now similarly, we can ask what is the effect of applying J minus on this state. So if I apply J minus on lambda m, and then ask what its J3 eigenvalue is, by using the other commutation relationship, we get m minus 1 times, sorry, this should be a J minus, not J1. There should be J minus lambda m. Okay? So this tells us that J minus lambda of m is proportional to lambda m minus 1, and we can call the proportionality constant dm minus 1. Okay? Any questions so far?
I didn't really understand how we get these, like this is proportional to that statement.
Right, sure. Yeah, so the idea is that, this thing, this state is an eigenstate of J3, right? So J3 acting on lambda and m gives me m lambda of m. Okay? Right? You got that, right?
Yes.
So now, if I have any state, let's call it psi, is equal to, say, C, not C, C is a bad, like A of psi, that's an eigenvalue equation, right?
Yes.
So, so now I want to ask, if I take for this state, psi, this state, J plus acting on lambda, comma, m, what is A? Okay? Using the knowledge, using this knowledge. Okay?
Okay, I see.
So now we are using, this is the state. This whole thing is the state. And what I've proved here is that if you apply J3 on it by using the algebra, you actually get another eigenvalue equation, but with the eigenvalue changed to m plus 1. So this state, the one in the bra, no, not the bra, the ket, this state has eigenvalue, J3 eigenvalue m, right? Over here, right, Saif?
Yeah, yeah.
But this whole state with the J plus acting on this is a different state, right?
Yes.
That state has J3 eigenvalue plus 1, m plus 1.
Yeah, that makes sense.
So the effect of applying J plus is that it increases the eigenvalue by 1. It takes us to a new state with a different eigenvalue.
Oh, I get it. Yeah.
Okay, yeah. And then we call that proportionality constant something, Cm plus 1. And similarly, if I apply J minus to this state, it decreases the eigenvalue by 1. J3 eigenvalue by 1. Okay, and I write that here with a new proportionality constant. C is for J plus, D is for J minus.
So these are kind of like ladder operators?
They're exactly ladder operators. That's my next statement. As you've seen in harmonic oscillators, right?
Yeah.
Yeah. So, basically, J plus has a name. It's called the raising operator. And J minus is called the lowering operator. In mathematics, their names are reversed, but mathematicians are weird. And this, together they're called ladder operators. Okay. So why are they called ladder operators? Because they do the following thing. So let's look at our vector space and let's line up our linearly independent states, the basis states, right? So these are the J3 eigenvalues of our basis states. These are the J3 eigenvalues. So suppose that M is here. Then M plus 1 is here. M plus 2 is here, so on and so forth. Here we'll have M minus 1, M minus 2, so on and so forth. Okay. So what happens is that the J minus operators, they take you down one step, one unit, right? Whereas the J plus operator, they take you up one unit. So that's why J pluses are called the raising operators and J minuses are called the lowering operators, and together they're called ladder operators because they allow you to move up and down this ladder of basis vectors. All right, so I hope the picture is clear.